Okay, good day everyone. So today we are going to discuss about the different laws of thermodynamics, wherein we will have first the zeroth law of thermodynamics and the first law. Okay, so let's start. Okay, let's define first thermodynamics. Thermodynamics is a branch of physics wherein this is the study of heat and its transformation to mechanical energy. And also it is about the study of relationships involving mechanical work, pressure, and temperature, and their roles in energy transformations. For example, we analyze how an engine works. So you can see here in the illustration, we have the temperature, we have the heat input, and then it will produce a steam, and then that will produce a work output, or it can be converted to mechanical energy. So the physics behind this, or behind how this one works, is about thermodynamics. In discussing thermodynamics, we will deal with thermodynamic system, wherein it's defined as a system that can interact with its surroundings or environment. And also, we will be dealing with, or we will be analyzing the different thermodynamic processes. So it is defined as a process in which there are changes in the state of thermodynamic system. So what could be those changes? It could be change in the internal energy, pressure, temperature, or the heat added or released by the system. It could also be the work done by the system or the work done into the system. It could also be a change in the volume. So those are the different thermodynamic processes. And then, as I have mentioned, thermodynamic system has an ability to interact with its surroundings or environment. Now, let's take a look at this by looking at how can we cool a house on a summer day. And let's relate that to thermodynamics. Letting heat flow from your home to your neighbor's home. So, ilipat mo lahat ng heat from your house to your neighbor's house. So, is that possible? Will the law of thermodynamics allow that? Okay, we will see. Now, let's just try to destroy some of your home's thermal energy. So, can we also do that? Or convert some of your home's thermal energy into electrical energy. Then, in that way, you can also conserve electrical energy, or that could also lower your electric bill. So, will the law of thermodynamics allow those things to happen? We will see. Let's analyze the first one. Can you let the heat flow from your home to your neighbor's home? So that one is related to zeroth law of thermodynamics. Your home is actually in thermal equilibrium with the outside air. And then since, let's say there's no air conditioning system, then it's in thermal equilibrium in the surroundings or with the outside air, and then no heat will flow from one to another. Your neighbor's home is also in thermal equilibrium with the outside air. If they are in thermal equilibrium, so they are at the same temperature, so you cannot let the heat flow from your home to your neighbor's home, since no heat will flow if the systems are in thermal equilibrium, or if they have the same temperature. Take note that the heat or the thermal energy can only be transferred if one system has higher temperature to a system having lower temperature. Okay. So, zeroth law of thermodynamics is stated as this: two objects that are each in thermal equilibrium with the third object are also in thermal equilibrium with one another. So let's talk about your house and your neighbor's house. House 1, it's in thermal equilibrium with the surroundings. That's C, or system 3. And then house 2 is also in thermal equilibrium with system 3. Since they are in thermal equilibrium with the system 3, therefore house 1 and house 2, they are also in thermal equilibrium. Okay? So that's what it means by zeroth law of thermodynamics. Why zeroth law? Because they were able to come up with this one after the first law of thermodynamics. So they just name it as zeroth law of thermodynamics. Okay, now let's talk about the first law of thermodynamics. can we just destroy some of your home's thermal energy so that it will not be very hot inside your house? You cannot cool your home by destroying some of its thermal energy, since energy, as you have learned in the mechanics, cannot be created nor destroyed. To eliminate thermal energy, you must convert it to another form or transfer it elsewhere. So you cannot destroy thermal energy. So again, that is impossible. Now let's move to the first law of thermodynamics. It is telling us that the change in a stationary object's internal energy is equal to the heat transferred into that object minus the work done by the object, or the work that the object does on its surroundings. I'll show you an equation later. First law of thermodynamics is also a generalization of the principle of conservation of energy, including energy transfer through heat and as well as energy transfer through mechanical work. It is a relationship between heat, work, and internal energy of a closed system. So this is our equation. We have delta U. Delta U there is the change in internal energy. So that's the final internal energy minus the initial internal energy equals Q. Q is the heat added to the system. And then minus work, that is the work done by the system. Now you have to remember sign conventions also in dealing with thermodynamics. Okay, let's analyze the signs. We have positive Q if heat is added to the system. Okay, for example, you have water inside a container which is covered, and then you add heat to the system. That is positive Q because heat was added to the system. But if heat is subtracted from the system, or if heat is released, let's say for example freezing, we know that in the process of freezing, heat is released. So that is negative Q. For the work done, if work is done by the system, how will that happen? If you have a container, then it is covered, then the water inside is boiling, you can see that the cover or the lid can move. So the movement of that lid, which is upward, that is the work done by the system. That is positive. But if there is a container wherein you can push the cover or you can compress it, that is the work done on the system. Okay, so take note of that. If work done by the system, that is positive. But if there is work done on the system, that is negative. Okay? So looking at this relationship, adding heat to the system can increase its internal energy. And doing work, or the system doing work, lessens the internal energy. But if you're doing work on the system, that increases its internal energy. If heat is released by the system, that is also decreasing its internal energy. Okay? So do not be confused with those changes in the thermodynamic systems. Okay, so now let's talk about thermodynamic processes. We have first, adiabatic process. No heat is transferred into or out of the system. So you can see here the graph of adiabatic process, wherein there was a change in the pressure and there was also change in the volume, but there's no heat added to the system. So you have here, let's take a look at the equation to describe this. From the first law, we have delta U is equal to Q minus work. But take note that for adiabatic, Q is equal to 0. Therefore, we can cancel this out. And then you now have here delta U, or the change in the internal energy of the system, is equal to negative work. Okay? So any work done by the system you can see it will be negative. So that is a decrease in the internal energy. But if there's work done on the system, let's take a look at work done on the system. We have here negative times negative work. So that will give you positive work done. So that means it increases the internal energy of the system. So since we already have mentioned that there's no heat added on the system or released by the system, so Q is equal to 0, we have here this equation. Okay, we have here this equation, delta U is equal to negative work. Okay, so that is for adiabatic process. Let's take a look at the next process. We have here, as you can see here, it's an isochoric process, wherein isochoric process is described as a constant volume process. So you can see in the illustration, volume is not changed. So you can also see here that there's no work done. So delta work is equal to 0 because when we say work done by the system, the volume can expand. Work done on the system, the volume can compress or can be less. But if there's no change in the volume, that means that there's no work done. So there's no curve here. Unlike for this one, let's take a look at the adiabatic process. You can see here, this curve describes the work done. But for this one, there's no work done because there's no change in the volume. So if we will recall the equation that we have here delta U. Okay, so let's recall our equation. We have delta U is equal to Q minus work. But for isochoric process, work done is equal to 0. So we now have here delta U, or the change in internal energy, will be dependent on the heat added by the system or the heat released by the system. That is for isochoric process. The next is isobaric process, wherein this one, pressure is constant. So you can see in the graph, we have point A and point B. The pressures are the same, but there is a change in the volume. So you have here V2 and V1. So using a PV diagram, that's a PV diagram, the area here would be the work done by the system. If we have here, volume 2 is greater than volume 1. So this is an equation describing the work done. Work done is equal to the pressure, volume 2 minus volume 1. And then we can also apply the first equation that we had, wherein delta U is equal to Q minus the work done. Okay. So this is still applicable for isobaric process. Next. Isothermal process, that means there's a constant temperature process. The work done by the system again is positive, and that the work done on the system is negative. Let's take a look at the graph. You have here point A to point B. There's a change in pressure. There's also a change in the volume, but there's no change in the temperature. But you have here from A to B, this area is the work done, okay, by the system. But for isothermal process, take note that for isothermal, delta U is equal to 0. So we have delta U equals Q minus work. So deriving the equation here, we have, since our delta U is equal to 0, we now have Q would be equal to the work done. That is for isothermal process. That will be our equation for isothermal process, okay? So we can also have here PV equals nRT, Since temperature is constant, and then N, then R is constant for a system that we are analyzing, therefore, if there's a change in P, let's say P increases, the volume should decrease. But if P decreases, the volume should increase, so that the temperature there will still be the same, or there's no change in temperature being an isothermal process. So as again, you can see here, volume is large, but pressure is low. And then volume is low, but pressure is large. Okay? It's like an object being compressed. For example, you have particles inside and then you compress that into a smaller volume, the pressure will be high. But if that is released into a higher volume or greater volume, the pressure with the same number of particles, the pressure will be lower. Okay? So that's the concept behind it. Okay, so let's try to solve the following problems. A system has an initial internal energy of 30 joules. 40 joules of heat is added to the system, and the system does 23 joules of work. What is the change in internal energy of the system? And then what is its final internal energy? So let's take a look at the equation. We have here delta U is equal to Q minus work. So the initial internal energy is 30 joules. Then 40 joules is added to the system, so that's positive. We now have here 40 joules. And then 23 joules of work, or the system does 23 joules of work. That's the work done by the system, so that is also positive. So it's minus 23 joules in our equation. So we just have here 17. The change in internal energy is equal to 17 joules. But change in internal energy is internal energy final minus internal energy initial. So that is 17 joules. The question here is what is the final internal energy? So that's final internal energy is equal to 17 joules. Then we have plus the initial is 30 joules. Or the initial, 30 joules. So that is equivalent to 47 joules. So that is now the final internal energy of the system, equivalent to 47 joules. Okay? The next item. In an isothermal expansion of ideal gas, the gas does 500 joules of work in the process. So that is, again, work done by the system. So that is positive. What is the change in the internal energy of the gas? And how much heat is absorbed during the process? If you are going to analyze this one, it's an isothermal expansion. So that is delta U is equal to 0. For isothermal, we have this, delta U is equal to 0, since there's no change in temperature. So that is for A. The change in internal energy of the gas is 0. How about letter B? How much heat is absorbed during the process? So you have delta U is equal to Q minus work. But for this process, as we have mentioned, delta U is equal to 0. So how much heat is absorbed? That's Q is equal to work. This is the work done by the system. So that is positive. We now have the heat is equal to 500 joules. The heat added to the system is 500 joules. However, the work done by the system is also 500 joules. That's why delta U is equal to 0. So there's no change in the internal energy of the system. Okay, next. An ideal gas has undergone an adiabatic. So that's adiabatic compression. During the process, 2000 joules of work is done on the system. How much heat flows into or out of the system? Take note that if it's adiabatic, Q is equal to 0. So that's our answer for letter A. The heat flowing into or out of the system is 0. But B, what is the change in the internal energy? We have delta U is equal to Q minus work. But for this one, our Q is equal to 0. Therefore, the change in internal energy is equal to the negative work done. So take note also that this one, work done, 2000 joules of work is done on the gas. So work is done on the system, that should be negative. So that's negative times negative work done on the system, which is 2000 joules. So you now have a positive 2000 joules for the change in internal energy. So this one means that the internal energy has increased by 2000 joules, okay? Since work is done on the gas and not work done by the gas, okay? So that's for number 3. Okay, let's have another problem. We have here an amount of heat equal to 2500 joules is added to a system and 1800 joules of work is done on the system. What is the change in the internal energy of the system? Letter B, what would be the internal energy change if 2500 joules of heat is added to the system and 1800 joules of work is done on the system? So let's solve. Okay, for the first one, for A, delta U is equal to Q minus work. Okay, so you have 2500 joules of heat is added. So that is positive. And then 1800 joules of work is done on the system. So that is negative. So negative 1800. So that would give us a change in internal energy, which is a positive 4300 joules. So that means that the internal energy has increased for letter A. Now let's solve letter B. Okay, for B we have again delta U is equal to Q minus work. Okay, again, heat is added, so that's positive, but work is done by the system, so that's positive also. 2500 joules of work, or 2500 joules of heat, minus positive 1800 joules. So that will give us 700 joules. So the change in the internal energy of the system is equivalent to 700 joules. Okay. Next. An ideal gas expands isothermally. So you have here isothermal process performing 4.4 times 10 to the third joules of work in the process. Calculate the change in the internal energy and calculate the heat absorbed during the expansion. So take note that it's an isothermal process, so there's no change in temperature, and change in internal energy is equivalent to 0. So we have here again delta U is equal to Q minus work, but since delta U is equal to 0, we now have Q is just equal to the work done. So Q is equivalent to, we have here, performing 4.4 joules of work in the process. So the gas expands and it does the work, so that is positive. Therefore, we have heat is also equivalent to 4.4 times 10 to the third joules. So that is the heat absorbed during the expansion. Next. In an engine, an almost ideal gas is compressed adiabatically to half its volume. When we say adiabatic, Q is equal to 0. No heat is added or released by the system. In doing so, 1,350 joules of work is done on the gas. So on the gas, so that is negative. How much heat then flows into or out of the gas? The answer for A is that Q is equal to 0 since it's an adiabatic process. But for B, what is the change in the internal energy of the gas? We have here delta U equals Q minus work, but delta U equals Q minus work, but Q is equal to 0. So we now have delta U is just the negative of the work. But here it's the work, it is compressed, and work is done on the gas, so that is negative. Okay, we have 1,350 joules. Okay, so the change in internal energy is positive 1,350 joules. So you can see there that delta U is positive, therefore the internal energy has increased and the temperature has risen. Okay, so the temperature has increased. Okay, so that would be all about first law of thermodynamics and all the problem solving. Now please complete the problem solving in the module. Okay, bye everyone, and in the next video we will have the second law of thermodynamics. Okay, see you in the next video. Bye.